everyone. Okay, so in this video we are going over de Moivre's theorem or de Moivre's theorem. I'm just going to say de Moivre's theorem because it's just easier. So we're going to be going over de Moivre's theorem. But before we do that, let's find out where de Moivre's theorem comes from. So if you recall, in the last video you watched, hopefully, the last video there we were looking over the multiplication and division of complex numbers in polar form. So let's just say here, I just have a regular complex number in polar form, or times cosine theta plus I sine theta. Right, so what happens now if I want to find z squared? So I'm multiplying this complex number by itself. Well, that's going to be or times or, which is or squared, times cosine theta plus I sine theta plus theta, which is or squared times cosine 2 theta plus I sine 2 theta. Right, let's do it again. Let's do the power of 3. So that's going to be or times or times or, which is or cubed. And that is going to be theta added together 3 times. It's going to be theta plus theta plus theta. That's going to be 3 theta. I sine 3 theta. Are we noticing a pattern yet? What about z to the power of 10? That's going to be or times or times or times or times or times or whatever, 10 times. So it's going to be or to the power of 10 times cosine, and it's going to be theta plus 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 theta, whatever, right? I'm adding theta together 10 times plus I sine 10 theta. Right, so what about if I just put it to a number like n? I multiply together n times. Can we generalize this? So this is what de Moivre's theorem is. If we notice a pattern here, right, if I have it to a power of 2, I put the modulus to that power, and then I times the argument by that power. So here, power 3, so it'd be or to the power, my modulus to the power 3, and then 3 times my arguments, right? What about power 10? But modulus to the power 10, and then times the angle by 10. So this is what de Moivre's theorem is. It just means for a power of a complex number z to the power of n, we just raise the modulus to that power, and then we just times the argument by that power. And that's it, right? So that is de Moivre's theorem. So de Moivre's theorem is used for computing powers of complex numbers. So if z is equal to or times cosine theta plus I sine theta, then z to the power of n, or power of that complex number, is or to the power of n times cosine n theta plus I sine n theta. So the proof of this theorem is covered in proof by induction. That will be in a later video, but let's have a look at this question here. Let z equal root 2 times cosine pi over 4 plus I sine pi over 4. Find the power of z to the power of 4. So z to the power of 4, what do I do to that power? Well, this is going to be root 2 to the power of 4. And then it's going to be cosine 4 times pi over 4 plus I sine 4 times pi over 4, which is going to be equal to 4 times cosine pi plus I sine pi. That's the answer there. And if you want to put it in rectangular form, it didn't ask us here, but 4 times cosine pi is equal to -1, and sine pi is 0, so 0i. So my answer here is -4. Right? How fun is that? Right. Let's look at some exam questions here. So it's very important when using de Moivre's theorem. It has to be in polar form first. It has to be in polar form. So root 3 minus I to the power of 9 can be written in the form a plus bi, where a, b are integers and I squared is -1. Use de Moivre's theorem to find the values of a and b. So I need to find this to the power of 9. Now, you could be a loser and multiply this bracket out 9 times, but like, that's crazy. That's wild. That's insane. So maybe don't do that. So let's use de Moivre's theorem. First, I need to convert this to polar form, right? So polar form, need to find my modulus. My modulus is equal to root 3 squared. Let me just rub this pen out, a bit too big. 4 is equal to root square root of root 3 squared plus minus 1 squared, which is equal to root 10. Modulus is equal to root 10. Then my angle is going to be equal to, so just plot this out here. So it's positive root 3 here, it's in quadrant 4. So that's going to be equal to tan inverse minus 1 over root 3, the absolute value of that, which is just going to be equal to tan inverse 1 over root 3. I do apologize for my dog barking. Hopefully you cannot hear. It is going to be tan inverse 1 over root 3, which is just equal to 1 over 6 pi. Therefore, my argument is equal to 2 pi minus 1 over 6 pi, which is my 11 over 6. That is my argument. So, in polar form, this is going to be equal to z is equal to, sorry, can I make this page a bit bigger? Right. Right. So z is going to be equal to root 10 times cosine 11 pi over 6, or 11 over 6 pi. So 11 pi over 6 plus I sine 11 pi over 6. Right, I'm going to calculate this now to the power of 9. So using the Moivre's theorem, it's just going to be the... Oh! Right, let's look at some exam questions now. So this is from 2022. So root 3 minus 1 to the power of 9 could be written in the form a plus bi. Use the Moivre's theorem, find the value of a and b. So we want to find the value of this. So we could like multiply out the brackets, but that's weird. That's stupid. That's ages. So let's use the Moivre's theorem. So this needs to be written in polar form first. So my modulus is equal to square root of root 3 squared plus minus 1 squared, which will be equal to root 4, which is equal to 2. Then my argument is going to be equal to, so this is going to be in the fourth quadrant. So theta is going to be equal to tan inverse. So it's going to be minus 1 over root 3, but we need to take the positive of it. So it's 1 over root 3. That is going to be equal to 1/6 pi. Therefore, my argument, 2 pi minus 1 over 6 pi, is equal to 11 pi over 6 on my calculator. Sub it in, I get z is equal to 2 times cosine cosine 11 pi over 6 plus I sine 11 pi over 6. Then I'm putting all this to the power of 9. So using the Moivre's theorem, it is going to be 2 to the power of 9 times cosine 9 times 11 pi over 6 plus I sine 9 times 11 pi over 6, which is going to be equal to 2 to the power of 9, which is 512. Cosine of 99 pi over 6. Put that in a calculator. That is going to be 0. Then sine of 9 times 11 pi over 6 is going to be equal to 1i. Therefore, my final answer is 512i. So A is going to equal 0, B is going to equal 512. That is my answer there. Right, let's look at this one. 2018. Find this in a simplest form. So it doesn't state to use the Moivre theorem here, but we're smart, right? We're very resourceful. We know to use the Moivre theorem. So I need to calculate my rate, my modulus, and my argument. So again, modulus is equal to minus a half squared plus root 3 over 2 squared, which is equal to 1 over 4 plus 3 over 4, which is going to be equal to root 1, which is equal to 1. My modulus is equal to 1. My argument then is going to be equal to, plot it out, so it's minus plus, so it's in the second quadrant. So theta is going to be equal to tan inverse of root 3 over 2 divided by minus a half, but we want it all to be positive, so I'm just going to divide by a half, and that is going to be theta is equal to, I think, tan inverse root 3, which is going to be 1/3 pi. Therefore, my argument is going to be equal to pi minus 1/3 pi, which is equal to 2 pi over 3. Okay, now I have my modulus and my argument. Let's sub it in. So z is equal to 1 times cosine 2 pi over 3 plus I sine 2 pi over 3. Right, so we're putting this to the power of 3 using the Moivre theorem. So it's 1 cubed times 2 pi over 3 times 3 times 2 pi over 3 times 3. That is going to give me z cubed is equal to 1 times cosine 2 pi plus I sine 2 pi. That is going to give me 1 times 1 plus 0i, which is going to be equal to 1. How fun is that question? Right? Simplified, it's 1. Let's try this one now. This is from 2017, so as you see, it comes up all the time. So, given z is equal to minus root 3 plus I use the Moivre theorem, write z to the power of 4. So, my modulus equal to root 3 squared plus 1 squared, which is equal to root 4, which is equal to 2. My argument is going to equal to tan inverse of 1 over just root 3, because we're taking the positive sense of it, which is going to be equal to 1/6 pi. My argument, this is going to be in the minus root 3, it's going to be in the second quadrant, so it's going to be pi minus 1/6 pi, which is just 5/6 pi, or 5 pi over 6. This is going to be equal to 2 times cosine 5/6 pi plus I sine 5/6 pi. So to apply the Moivre theorem, we want to find z to the power of 4. So power of 4, bring the power to here, times my argument by 4. This is going to be 2 to the power of 4 is 16 times cosine 20 pi over 6 plus I sine 20 pi over 6. So 16 times, multiply this in now, it's asking us. So cosine of 20 pi over 6 is equal to 16 times minus a half plus sine 20 pi over 6, which is going to be plus I times minus root 3 over 2. That is going to be equal to minus 8 minus 8 root 3 I. That is my final answer there. Right, again, let's keep trucking along. 2016. So use the Moivre theorem, express 1 plus I to the power of 8 in its simplest form. So my modulus is just going to be equal to 1 squared plus 1 squared, which is equal to root 2. My reference angle is going to be tan inverse 1 over 1, which is just going to be a quarter pi. And we're in the first quadrant. Therefore, my argument is equal to a quarter pi. So, sub them in here. Root 2. So, z is equal to root 2 cosine a quarter pi plus I sine 1 quarter pi. I want to put this to the power of 8. So times this by 8 times this by 8. So I have root 2 to the power of 8, which is going to be equal to 16, times cosine of 2 pi plus I sine of 2 pi. So this is going to be 16 times 1 plus 0I. So my final answer is just 16. How fun is that? Oh, love that. Right. 2 more questions. Let's go. So let z equal 5 over 2 plus I minus 1. So express z in the form a plus bi and plot it on an Argand diagram, and then use the Moivre theorem, evaluate z to the power of 6. So this is going to be equal to 5 minus 2 minus I all over to 2 plus I. So we have a minus 1 here. That is going to be 3 minus I all over 2 plus I. Multiply the top and bottom by 2 minus I, the conjugate of my denominator. So when you multiply at the top of this fraction, you're going to get 6 minus 2I minus 3I plus I squared all over. Multiply this out, you're going to get 5. So here, I'm going to have 6 plus I squared. It's going to be 6 minus 1, which is 5. 5 minus 5I all over 5, which is equal to 1 minus I. So that is this simplified out to 1 minus I. So now let's evaluate it for the power of 6. So now let's find z to the power of 6 within the question. So my modulus is equal to 1 squared plus minus 1 squared, which is equal to root 2. And then my argument is equal to tan inverse minus 1 over 1. Remember, we have the positive sense of this, so it's going to be tan inverse just positive 1, which is just a quarter pi. Then we are in the 1, 2, 3, 4, bing, bing, bing. We're in the fourth quadrant because we have a positive real number, negative imaginary number in here. So my argument is going to be 2 pi minus a quarter pi, which is equal to 7 pi over 8. So 7 pi over 8. So I have root 2 times cosine 7 pi over 8 plus I sine 7 pi over 8. That is my complex number in polar form. But we're looking for z to the power 6. So put to the power 6, my mod to the power 6 times the arguments by 6. So I have here 2 to the power of 6 is going to be equal to 8 times cosine 21 pi over 4 plus I sine 21 pi over 4. So cosine 21 pi over 4 is equal to 8 times minus root 2 over 2 plus I times sine 21 pi over 4, which is just minus root 2 over 2. That is going to give me minus 4 root 2 plus 8 to the minus 4 root 2I. And that is my solution there. Last question. It says in 7, let minus 1 plus I. So use the Moivre theorem, evaluate z to the power of 5 and z to the power of 9. So, in polar form, right? Polar form, I've been doing polar form all videos, so let me have this one. It's going to be equal to root 2 times cosine 5 times, nope. Right, so we got our complex number simplified there. So let's get it in polar form. So or is equal to the square root of 1 squared plus minus 1 squared, which is going to be root 2. My reference angle is going to be tan inverse of the positive, or the absolute value of minus 1 over 1, which is just tan inverse of 1, which is just 1/4 pi, or pi over 4. So my actual argument, however, this is in the 1 minus I, it's in the 4th quadrant. So therefore it's going to be equal to 2 pi minus 1/4 pi, which is equal to 7 pi over 4. So now that I have my argument and my modulus, let's find z to the power of 6. So z is equal to root 2 times cosine 7 pi over 4 plus I sine 7 pi over 4. So I want to find z to the power of 6, so I put my modulus to the power of 6, and I times my argument by 6 using the Moivre's theorem. And I have here 2 to the power of 6, which is equal to 8. Cosine is going to be 21 pi over 2 plus I sine 21 pi over 2, which is going to be 8 times 0 plus I, and my final answer is just 8I. How fun is that? Right. Now let's move on to the final question here. This is 2007. So use the Moivre's theorem, evaluate z to the power of 5 and z to the power of 9. So again, modulus is equal to 1 squared plus 1 minus 1 all to be squared plus 1 squared, which is equal to root 2. Then root 2, my reference angle is going to be equal to tan inverse 1 over minus 1, the absolute value of all that, which is just equal to tan inverse 1, which is equal to 1/4 pi. Then let's calculate my argument. I am in quadrant 2 here. So my argument is equal to pi minus 1/4 pi, which is just 3 pi over 4. So z is just equal to root 2 times cosine 3/4 pi plus I sine 3 pi over 4. Okay, so let's apply the Moivre's theorem. Z to the power of 5 is going to be equal to root 2 to the power of 5 times cosine 15 pi over 4 plus I sine 3 pi over 4 is just 15 times 5 is just 15 pi over 4. Evaluating this out, we get so square root of 2 to the power of 5 is gonna be equal to 4 root 2. Root 2, and then cosine cosine 15 pi over 4 is going to be equal to root 2 over 2 plus I times minus root 2 over 2. Multiply this in and you'll get z to the 5 is equal to 4 minus 4i. That's z to the 5. What about now z to the 9? That's going to be root 2 to the power of 9 times cosine times 9 times 3 pi over 4, which is going to be equal to 27 pi over 4 plus I sine 27 pi over 4. This will simplify down to 16 root 2 times minus root 2 over 2 plus I times root 2 over 2, which is equal to z to the power 9 is equal to minus 16 plus 16i when you multiply it in. So I have z to the 9, z to the 5. The last part is show that z to the 5 plus z to the 9 is equal to 12z. So let's add these together now. So 4 minus 16 is just minus 12. Minus 4 times minus 4i plus 16i is just minus 12i. If I factor out a 12 here, I'm left with minus 1 minus I. And if you look, oh, so that's plus 12. I'm left with a minus 1. 12 times minus 1 plus I, which is equal to 12 times my original complex number, z. And therefore I've proven z to the 5 plus z to the 9 is equal to 12 times z. Right, a bit of a long video, but I hope it helped. I'll catch you guys later. Hope the video was some help, and see you guys later. Bye.